Just about ready to get started. Okay. Good afternoon, everybody. I'm very pleased to welcome this week's colloquium speaker to the CFA colloquium series. Keith Gendreau, who will be talking today, did his undergraduate work at Cornell and then went to MIT, where he did a thesis on studies of CCDs with a view toward the utilization in space. And after that, went to Goddard Space Flight Center, where he's engaged in a very ambitious and visionary program of development, which goes all the way from immediate needs of detector calibration and detector development, all the way out to very visionary, far future, ultra high resolution missions in the direction of black hole imager and MAXIM. And in the particular example that he's going to present to us today, which is the NICER mission, he's done a very clever combination of different aspects of space science, which focuses scientifically on the studies of neutron stars, but combines that also with space navigation and a very advanced use of X-ray timing capabilities. And for those of us who have experience with the space program, he's pulled off a particularly impressive stunt, which is combining space sciences with the use of the space station, which involves a lot of, I hear that there's a lot of resonance with that here. So Keith is going to tell us about the progress with the NICER mission, and welcome, Keith.
Thank you very much. So NICER stands for the Neutron Star Interior Composition Explorer. I'm going to tell you about our mission and how we managed to marry Science Mission Directorate, NASA headquarters, Space Technology Mission Directorate, NASA headquarters, and the ISS. So we are a mission of opportunity on the space station. Our primary science is to study, understand ultra-dense matter through soft X-ray timing of neutron stars. Our launch is on one of the resupply vehicles that goes to the space station. We're currently slated to go on SpaceX 11. So this is a Falcon 9 rocket we're going on. And before yesterday, I would tell you that we're launching in January. And before a week ago, I would have told you we're launching in August. We're ready for a launch in August. Yesterday, we heard rumors that SpaceX 11 might be moving out to March. So I have a meeting tomorrow to see how real that is. Once we get to the space station, we're going to be mounted over here at one of the Express Logistics Carrier, or ELC slots. And this is a picture of what NICER might look like in a deployed configuration at that spot on the International Space Station. We're up there right now. We're approved for 24 months. 18 months is for our baseline science mission to study neutron stars. We have 6 months for a guest observer program. And then we get into the senior review process, where hopefully we'll have an extended mission beyond that so that more people can use NICER to do timing astrophysics from the space station. The instrument itself is a X-ray concentrator-based system. We use X-ray concentrators to focus X-rays from our pulsars onto silicon drift detectors. We measure the photon energy, each photon, to about 2%. And we measure the arrival time of every photon, absolute compared to a GPS time standard, better than 100 nanoseconds. We are a mission class D in NASA terminology. That means we get a little bit more say in balancing risk against cost. And we took advantage of that to fit within the cost bracket that we have to build the NICER instrument. In addition to the guest observer program, we have an additional technology enhancement, and that is to demonstrate pulsar-based navigation from the International Space Station. About a quarter of our funding comes from the Space Technology Mission Directorate to do this demonstration. We actually just last week, we formally got into Phase D. We had completed our EMI EMC testing, and by the end of this talk, we will have shaken the flight payload in one axis. And tomorrow we do the next axis, and over the weekend the z-axis. Next week we move to thermal vacuum. So we're well along and working as if our launch is still in August. So our primary science objective is to measure the radius of a neutron star through soft X-ray timing. I'm not going to go over all the details here, but we're using a number of techniques of X-ray light curve modeling, some of which were developed by Slavko Bogdanov, who was here some years ago. And we believe that with these methods and with our instrument, we should be able to measure the radius of a neutron star to about 5%. And depending on who you speak with, this is an order of magnitude improvement in the state of the art, which allows you to produce an error bar in an equation of state diagram that relates the mass to the radius of a neutron star that's very small. And for example, for one of our primary targets, JO437, could give you an error bar that would rule out a number of models that describe the physics governing the interactions of particles at the core of the neutron star. So we're doing this with an instrument which has, I think, an unprecedented combination of three really good characteristics. We have, in one package, very good energy resolution, CCD type energy resolution, about 2% energy resolution. We have time resolution, which is an order of magnitude better than it was on any other mission. We can absolutely timestamp every photon to about 85 nanoseconds, all the way, including all of our systematics, all the way to a FITS file that you would eventually use to analyze your data. And because we're using concentrating optics, we have very high sensitivity. So the last state-of-the-art X-ray timing mission was the Rossi X-ray Timing Explorer, which lasted for 16 years, was turned off more or less kicking and screaming, with actually a tremendous science output. Over 2,700 peer-reviewed papers came out of that mission. NICER overlaps its bandpass. It concentrates at the low energy end for neutron stars, but will have improvements by an order of magnitude in these three characteristics of energy resolution, time, and sensitivity. And just as a comparison, this is our current estimate of what the peak effective area that we're going to get in this package is compared to the XMM Newton PN CCD, so the part of XMM Newton that has good time resolution. So this is a little guided tour of what the payload looks like. No blankets are shown here, so you can see all the guts, and this is in its deployed configuration. I'll start from the top. The box structure is what we call the X-ray timing instrument, or XTI. It's a box that has at one end 56 X-ray concentrators, and I'll show you this in a second. Each concentrator has a dedicated silicon drift detector at the other end of the box. Underneath the box, we have a base plate where we put all of our avionics boxes. So we have our own star tracker. It comes from the Danish Technical University. We read that out at a very high update rate of 8 frames a second. We use that to control a 2-axis gimbal that you see here using flight software that's on our own main electronics box that basically tries to close the loop with the star track data so that we can point to somewhat better than an arc minute. And so that's something you should take away. This is an arc minute type astronomy mission on the space station pointed platform. We have our gimbal control electronics. We have all of our detector electronics are also in the back here. The 2-axis gimbal has been modified. It's a stepper motor. It's a standard stepper motor product from Moog, but we've optimized it so that we can minimize detent force while maintaining torque constant so that we can point this thing very smoothly and we don't actually have jittering. That 2-axis gimbal is on a boom, which is again connected to another deployment actuator and a locking actuator, which allows us to swing out above space station to give us a clear view of the sky. So the instrument can basically point anywhere in a hemisphere above the space station. except for a keyhole around the primary axis. It's about 10 degrees wide. The base of this, the deployment and pointing system, is connected to an adapter plate in green, and that adapter plate in green is connected to this gray structure, which is what we call an AFRAM, or an active flight releasable attachment mechanism. When you work with space station, there are a lot of acronyms that you learn, and so this is one of them. AFRAM is provided by space station. It's our mechanical and electrical interface to the launch vehicle, as well as the space station. And so it's got a lot of standard features. You can grab it by this structure that you see right here. There's a 7/16" hex nut in there that is a standard size for all the robotic tools on space station. So you turn that, it puts a cam in place and it locks your active FRAM to the passive FRAM that's either on your launch vehicle or the space station. There are blind mated electrical connections. Space station and the launch vehicle give you multiple flavors of power. There's 120 volt DC power and multiple circuits, and 28 volt DC power. We have a 1553 connection and a one-way Ethernet link for data download. Let me see. There's a few other things here, but I want to move on. So we have a fantastic team that put this together. There's a lot of people at Goddard, obviously, but there are some folks here today from MIT that make up our detector team. The detectors themselves come from Amtech, but MIT built all the system around making those detectors perform like we need for NICER. We obviously work very closely with the space station folks from the very beginning to make sure that we fit and that we're not violating any of their rules. Moog Broad Reach provides our avionics boxes apart from the detector electronics. And Moog again provides our actuators. Danish Technical University is providing our star tracker, and it's a fantastic star tracker for pointing this instrument. We're going to go up on a Falcon 9 rocket, and SpaceX 11 is our launch vehicle. So at the top of the Falcon 9 rocket, there's this Dragon capsule, which is a pressurized compartment that brings up food and that type of supply for the inside of the space station. Attached to it is this thing called the external unpressurized trunk. And in the trunk, we're going up with two other payloads. This is where NICER will be. And they're also attached by this standard FRAM mechanism that we're using. So when we go up, we only get power from the Dragon capsule to maintain survival heaters. We get no telemetry. So we launch, we have no telemetry for a while. We get to space station. We have lots of models about how we're doing thermally before we're installed. But basically, we just have power. Now, as I speak, you'll see this animation go through the steps of how we get from the trunk of the Dragon, and we get robotically moved all the way to this spot on space station. It's a picture of where we're actually going on the space station. From the beginning, we've been orchestrating all these moves. Space station has a very detailed CAD model that includes a lot of the dynamic motion. It's good to about a quarter inch, half inch or so. And so they tell us at what points we're getting close to other things, and we try to nip and tuck. And we've designed a payload which we can get from A to B. This is going way faster than it actually will. This will probably take 6 to 10 hours. One of the more challenging parts of this, this installation process kind of translates to a system engineering challenge that we have. That we get survival heaters in the Dragon going up. We get survival heaters when this is the robot that's at the end of the robotic arm. We get survival heaters when we're attached to the foot of this robotic arm. But when we are held by the actual arms themselves, we have no power. And you can get very cold in space with no power, and you could be at the end of one of these arms for up to 6 hours. That's kind of their con ops plan. So you have to design an experiment that can stay above its survival limits for up to 6 hours with absolutely no power. And And we've done that. So we've kind of expanded the survival limits of most of our major components, but it comes down to electronics. So our electronics, we store them on a panel that's got a phase change material, basically an engineered wax that melts at -10°C. And so we melt that wax and we get an extra few hours from that to stay above our survival limits. Adds some mass to our instrument. Once we're there, we go through a deployment process like you see here. We had to work with the safety office at Space Station to make sure that we had the right kind of mechanical inhibits, because we get very close to the solar panels, within a few feet, and you might have seen that there's a little thing about a hook here. That hook's there, so otherwise there's some multiple failure possibility that we could swing into the solar panels during deployment, but we had to put mechanical constraints in place to keep that from happening. This is again going way faster than we normally would, but our mode of operation is to pick up an object as it rises, track it until it sets, or we're about to get obscured by some sort of space station structure, slew to the next object, and so on. And we'll basically be tracking between 3 and 4 objects in orbit. We also have to have the capability to restow, because they want to have the opportunity to take you off of Space Station once you've been there for a while. And there are also some other safety concerns that astronauts will come out. There are dockings that you have to account for. There's a little jolt when a large spacecraft will dock with the space station. And, to again have suitable margin, we have to restow during those events. Our mirrors have got some sharp little edges in the front, and that's another reason for stowing. So when the astronauts go out, you don't want to be the experiment that cut an astronaut's suit. We've done a lot of modeling of what kind of astrophysics we can do from the space station. We have about 250 objects that we've modeled. We did a study where, and this animation is showing a little piece of part of that study that we did. We're very close to these solar panels, and so they're moving. And so one of the first thoughts I had was, how much time are we going to be doing astrophysics on space station that's not blocked by some of the space station structure? The solar panels stay locked to the sun, and that once you get through that, you realize that you can actually have a very high observing efficiency on station. If you include slews, you include the fact that space station's not in the best orbit for astrophysics. It's a high inclination orbit. Radiation belts give you background. If you take out those periods of time, there's also bits where the astronauts go out, or there are vehicles that are coming to bring supplies. If you take out all those times, including our slew times, we have an overall observing efficiency on space station of 54% to do astrophysics with a pointed experiment. So if you're going to plan a mission, that's a good number to have in the back of your mind. Our science requirements for our level 1 requirements are met with 33% efficiency, so we have margin there that will enable the guest observer program that we want to do. There's a lot of established infrastructure and well-defined interfaces which help to make this an instrument that you can build on a budget. I just talked to this, but this is part. We did to kind of prove that we can do our science. We took 200 known objects that we know we want to do astrophysics with, our neutron star science, plus calibration targets that are usually used, and we sprinkled in another 50 random targets. And we took the worst time of the year where the galactic center is, behind the sun. And over a 3-month period over this time, we simulated the view to every one of these objects in 1-minute steps and made an observing plan. And that's where we got our 54% observing efficiency with all the other terms. Actually, there's always objects to look at. It's kind of obvious, but but we had to actually simulate this. People don't like risk, and so we have to prove that we can do the science up there, and that's one of the things we did early on. I want to get into some of the components. So we're using, like I said, Amtech silicon drift detectors. So Amtech's not too far from here. They make detectors for X-ray fluorescence analysis. and not timing astrophysics. I'll talk about this later, but it's a very nice detector that you can buy. Here's the silicon drift detector. Underneath it, it has its own thermoelectric cooler. So you can cool each detector to the operating temperature, about minus 55 that we're doing for NICER. It's actually enclosed in a cap that's hermetically sealed. And NICER works all the way down to 200 electron volts. So how do we do this? We have a very thin silicon nitride window. It's 400 angstroms thick with 300 angstroms of aluminum on it to block light. This allows X-rays to pass all the way down to, they use the Amtech to look at beryllium K X-rays at 100 EV. Works for us to our requirement of 200 EV. And the amazing thing is you could put 2 atmospheres on this and it ain't going to break. It's fantastic. And actually having that capability, having your detector be coolable and all in one little package makes our integration and test program very easy. We can always test these things. We don't have to put the whole thing into a pressure chamber. So this is actually a good thing. I mean, Amtech doesn't make these things for spaceflight. And this is part of why being a Class D mission at NASA is good. We can buy these things. We could buy a lot of them. We can screen out the rejects. And because we have enough redundancy in our system, we can tolerate the risk of losing up to 20 of these things and still meet our minimum science instrument requirements. Like I said, MIT takes these detectors, they build a package that includes this mechanical hardware plus a preamp and some other shaping electronics that are elsewhere, and they put all these together just down the road at MIT. Every one of these detectors had hundreds and thousands of hours of operating time during their calibration and screening process. This is after MIT delivered all the detectors. This is before the harness was all dressed, but all those detectors are put into the back of our optical bench. And so actually, this is just a picture from about 2 weeks ago. You can see the telescopes at one end, and each telescope has got a detector at the far end. And if you look closely, you see that we've added some little black tubes to the top of each one of these detectors. These tubes restrict the field of view of the detector to its optic. So we wanted to minimize background, including background from neighboring X-ray telescopes. The tubes are actually really bulky. They've got it's aluminum with a few hundred microns of gold and a few hundred microns of silver to block hard X-rays from coming in through the side and introducing background. In addition, we have, it's a little hard to see, but there's some little lead collars at the base of each one of these, and that's because one of our larger background terms is actually from the Russians on space station. So the Soyuz spacecraft use roughly a 1 Curie cesium-137 source as a backscatter tool to trigger a little booster that fires when the spacecraft is about 1 meter above the ground. Unfortunately, it's always on, and when it's not backscattering against the Earth, it's backscattering against the service module that's connected to the landing capsule of the Soyuz. And at 40 or 45 meters away, which is where we are for these things, it actually contributes a lot of background. We learned about this because there's a Japanese experiment called MAXI that's up there, and they could see their background rate change in correlation with the number of Soyuz on space station. And so we've taken that lesson and we've put extra lead and we've modeled this really out the wazoo, and I believe we have this adequately shielded at this point. Now on to the concentrators. So this is a picture of one of our X-ray concentrators. It's about the size of a coffee can, and it has heritage from Goddard's thin foil X-ray optics program that's been around for about 30 years. It's got some differences. It's smaller than most Goddard X-ray optics, 10 centimeters by 10 centimeters roughly. It's a very short focal length. The short focal length is driven by the fact that the volume that we have on space station to do our science is only so much, and so this is the the tallest X-ray mirror that we could put in there. So we put 56 of these mirrors in to build up the area that we have. These are single shell optics, single reflection, so we don't have a primary and secondary mirror, so it's not imaging. And we feel this is appropriate for isolated point sources and actually gives us a large collecting area per kilogram. The other thing that's different with nicer optics is, unlike most Goddard X-ray optics where they use a conical approximation to the ideal parabolic shape, we actually have formed and replicated parabolic shapes for these optics because the focal length is so short, the conical approximation starts to break down. And so we actually have a parabolic shape to give us a good point spread function, which we need in order to have the sensitivity that we demand. We've done a lot of things to improve the process and how we make these things. We had to make them full shell to make sure we make maximum amount of area. Each one of these optics weighs only about 300 grams and provides about 50 square centimeters of area at peak. So we fit 56 of these, so you can get an idea of how this scales. And here it scales up to 56. This is the first 56 that we made. We actually built 70, and we calibrated every one of these things. We had a beamline facility at Goddard where we put these in a row, and we would just kind of step through them. So we have lots of good statistics about the spread of how these optics behave. And we picked the best ones, and it's going to improve, how you model the calibration of this instrument. So we have an optical bench, and this is a picture of the optical bench before the base plate was put on. That's designed to hold these optics and detectors and maintain alignment while surviving things like launch load. So we did a detailed structural thermal optical performance analysis. So we looked at, we modeled different types of, different orientations of this instrument on space station to track different pulsars through some extreme ISS thermal environments. We modeled that and put appropriate heaters to do some software control heating and put enough structure in place so that we maintain the alignment so that the overall instrument still can work at the arc minute level. We in fact tested it in the ground, so we, under ambient conditions, we watched the distortion as we put in a heat source and compare that against the model that we developed. And so we feel very comfortable that we're going to maintain the alignment, which is important if you have 56 telescopes to get your full area. This is the optics actually being staked, but they were installed and aligned under, this is a picture of a 1 meter collimator tower that we made. It's a 1 meter F5 mirror that generates a 1 meter diameter collimated beam. Optical light will go through our X-ray optics. We put a power meter at the bottom. We tip tilt each one of these optics to maximize the flux and then lock it down. And the 1 meter optic almost covers the entire instrument, so we have to move it twice to make sure that all the optics are co-aligned. When we finish all of our environmental testing, we're going to come back to this tower and verify that everything is still aligned. That's part of our program. We've done this actually at regular cadences. We did some subsystem testing that we double-checked that our mechanical design was good enough to maintain alignment. Oops. And I don't know. Unfortunately, I thought I checked all the videos, and actually, I don't know why I'm hearing sound. Oh, it's because I'm using an HDMI. Okay. So the video that you didn't see here was we built a structural verification unit, basically an identical copy of our flight optics, a flight optical bench, and we did that because when you work with SpaceX, they give you extremely conservative loads for shaking, and their contract with Space Station is not to provide coupled load analysis, which generally lowers the loads that you're going to test your hardware to, until 12 months before launch, which is kind of incompatible with our build schedule and building in general scientific instruments, right? So we built an identical copy of our optical bench, and we tortured it at those levels. We actually have, this is our flight deployment and pointing system attached to that, and the video that you would have seen was a sine burst test where we're strength testing it, and you'll see what I mean by conservatism, right? If you could see the video, and I apologize I didn't check that one, didn't work. Some of our avionics boxes and other components here. This is our flight main electronics box built by Broadreach Engineering. Handles all of our CNDH, so it talks to the space station, it talks to all the other subsystems. It also has power switching capabilities, so we can turn on one of our detector electronic slices or the star tracker or the gimbals. It also has a GPS receiver, which can provide us 10-meter positions and 30 nanosecond timestamps. And then it distributes that time to all of our instruments, including our science instrument. So our gimbal control electronics, modeled on one that is flying on LRO right now, and this is the star tracker made by DTU. The camera head is only this big, and it's quite fantastic. The electronics are only slightly bigger and actually can run 4 of those camera heads. And DTU worked with us to actually update their normal reset rate from about readout rate from 4 readouts a second to 8. We need that because we're on the space station, which is sort of a vibrating structure. We wanted to basically beat down that term in our point and control software. So we have a good, fast update rate for the star tracker. We've done a lot of testing with that full system. So this is actually EM hardware, but basically identical. That's our main electronics box EM, and that's our EM engineering model, gimbal control electronics with an EM gimbal system with an EM star tracker and some interns that are not EM that were used to actually do some really important work for us. We had a lot of, I like having interns involved in our programs, and so these interns did fantastic stuff. They did a really high fidelity test of the pointing system. We could project onto a screen under very stable conditions what the sky would look like from space station, and we could have it move ever so subtly to simulate the space station motion, and we could track and verify that our point and control software from beginning to end was doing the right thing. We did more quantitative measurements of the mechanical performance qualities of our optics, stiffness and stuff, using the actual flight hardware as well as some of the EM units on air-bearing tables, which I'm not showing here. This is in September. We had gotten all of our detector electronics, and MIT had just delivered all of our detector electronics. We integrated the entire X-ray timing instrument with those final bits, and then we went into our thermal vacuum test. And so here's a picture of basically most of the payload going into our vacuum chamber. Here's the detector electronics. Each detector's got 2 cables, so it's a real interesting swarm of harnesses that come out. And we ran this thing for about 2 weeks over the extremes of the thermal cases that we imagine. And we had iron 55 sources in there to verify that everything was working properly. So this is from one extreme thermal cycle of about 75 degrees. This is co-adding 56 detectors over this very wide temperature range that our electronics went under. And our requirements are to, I'll show you the requirements in a bit, but we're easily meeting our energy resolution requirements with this instrument. We verified it here. And actually, here are our requirements. We have to have better than 200 EV above 2 kilovolts, or I'm sorry, 1 kilovolt, and better than 120. And this is actually what we're achieving full system. The red curve is what MIT got at the subsystem level down the road, but when you fold in everything, including all the thermal all the temperature gain corrections that we have to do, we do slightly worse with the red curve, and again, it's meeting our requirements. This is actually from this weekend. We Finished our EMI, EMC, so electromagnetic interference and electromagnetic conductance test. And we started putting on our blankets, and our avionics boxes are now covered by radiators. There's some orange tape that's protecting some silver Teflon. We're going to peel that off next week before we go into our final payload TVAC. But this is the instrument in a deployed configuration. You can see our adapter plate, a few other components down here, and a simulator for the FRAM. The space station actually doesn't allow us to do our environmental testing with the flight FRAM because they've had some bad issues in the past with other payloads, and so we have to actually make a simulator for that. But you see that this cart's on wheels. And here's our 2-axis gimbal. We actually showed that we can actually, deploy this thing and nothing catches. It seems kind of trivial, but at this point, if there's a problem, it costs a huge amount of money and time to fix it. So here it is, actually closing a little bit, and our sunshades. These are the flight sunshades were put in, and that was like the last thing that we, weren't sure about. Would it catch? And hopefully the video is working. So this is actually a time lapse from Sunday of this actually working. And we, this table is very level because while our actuators can move our 500-pound payload in orbit very easily on the ground, they don't have enough oomph, and we're afraid about damaging them if we try to do anything against gravity. It was kind of this. Quite fantastic to watch this work for the first time this weekend. And here you'll see it close up in a second from the other side. Yeah, I'm sorry if this is very exciting for me right now. There's a lot of making sure nothing hitting and rubbing and all of that. That's that's me in one of those bunny suits going underneath, looking through the little hole that we had there. So I'm the PI and I'm responsible for this, and I'm involved in every aspect of this mission. Making sure this hardware comes together right. It's important. Our primary science is X-ray timing. And if you were at the lunchtime talks today, I talked about our modulated X-ray source technology that we've developed at Goddard. We've made X-ray sources that we can modulate. They're photoelectrically driven X-ray sources. You can turn them on and off or do arbitrary light curves. You basically can make any kind of X-ray light curve you want. And over here I have 2 of them configured with to produce copper K and zinc K X-rays. They shine through our optics and down to our detectors. And in another configuration, we had one shine up with the box upside down to the detectors up here. And with this, we could actually verify our timing calibration at the full system level. So our time comes from GPS. And so we have a GPS constellation simulator that generates the RF that a constellation of GPS satellites would produce as seen from a spacecraft in a particular orbit. That RF was piped and transmitted into our antennas, our GPS antennas, and our GPS system, figured out the time from that, generated a pulse per second, sent that pulse per second to every one of our detector electronic slices. Our detectors detected the pulse X-rays using a local oscillator on each detector electronics slice. It kept track of what that local oscillator's time constant was relative to the PPS coming in and broadcast by the GPS system. And then we produced data that became a FITS file that used all of our algorithms that we've pushed to this time to put a timestamp in it. So it's a real system, full system, end-to-end calibration of how the timing system works. And our requirement is 100 nanoseconds, and we actually got to 85.5 nanoseconds, full system level. And this is the spectrum. You can see the copper and zinc lines. And this is over 56 detectors. So again, we know this is, we know that the things that matter for timing and spectroscopy are working. I don't have a slide for this, but Gregory Prigozhin, who's here from MIT, brought our reference detectors out to the Berlin electron synchrotron Bessey for calibration, absolute calibration, and that you're putting electrons in bunches around this ring and producing synchrotron radiation that you're calibrating against. Those detectors could actually see the pulsed X-rays, the bunches of electrons in the synchrotron ring. And they're very tight. They're only a few picoseconds. So the absolute time resolution of just the detector system for at least our fast chain was about 64 nanoseconds, and for the slow chain, 74 nanoseconds. And so we know we have an instrument that meets our timing requirements. We produced one of these, actually a couple of these X-ray sources, modulated X-ray sources, to go to MIT. And these X-ray sources were configured to shine against a target that had fluorescence targets, Teflon, copper, aluminum, and titanium. So we could produce pulsed fluorescent X-rays. So they did about a 10 nanosecond wide X-ray pulse at a 600 kilohertz rep rate, right? And you got fluorescent X-rays like this. And if you take data with the flight detectors and the measurement and the detector electronics, you could do these folded curves where this is folded time and this is energy. And you can see carbon K X-rays down here, fluorine, all the way to the copper X-rays. And in this axis, you can see that we're achieving, I'm not fitting anything here, but you can see we're easily, in the 70 to 80 nanosecond range for timing resolution. So this source was used on every one of our detectors to give us energy response calibration and time calibration at the same time. Our program is very fast in order to keep the cost low, so we couldn't do a timing test and an energy test and a quantum efficiency test. We had to combine them. And this modulated X-ray source technology and ingenuity at MIT made this happen. At Goddard, we have our own little X-ray beamline. We have a 100-meter beamline. And like I said, every one of our X-ray optics was tested there. We have some other support equipment to do X-ray reflectometry measurements to basically verify our models for how the optics perform. And this is a histogram of going through 70 of these optics. This is a histogram of what the collecting area was at 1.5 kilovolts. Our requirement was to have an average of this level, of this level, but we actually got much better than our requirement demanded. And we had a CCD imaging detector there, so we could actually measure the point spread function, which is important to understand the sensitivity in the background. And so we easily met our requirement for concentration of the point spread function. So we capture about 90% of our photons into a 2 millimeter aperture, which is the aperture of on top of our detectors. And likewise, we could also test our ray tracing models. So the top is data, the bottom is ray tracing, and so we're actually still evaluating this, but the message I want you to walk away with is that we spent a lot of time on a shoestring budget to do, I think, a very good calibration of this instrument. So we were a mission of opportunity to the Science Mission Directorate because we're going to the space station. So space station operating budget provided us a ride that SMD didn't have to pay for. And we have access to a lot of infrastructure, ground systems and stuff, which makes this an opportunity. But I think we were more than the average opportunity because about the time that we were putting our proposal together, the Space Technology Mission Directorate, it's a different part of NASA that's all about technology, gave us funding. They provide about a quarter of our funding to see if we could use NICER to do a pulsar navigation demonstration. And for this navigation demonstration, we're using millisecond pulsars, which is conveniently exactly the objects that we want to look at for our prime science. So we could come up with a science program that could accomplish both of these things and and get a quarter of our funding to boot for it. And very important, STMD actually gave us a lot of money up front. So during our phase A, we got about $2.5 million from them. You know, if you're an explorer mission of opportunity to do your phase A study, what you get from SMD is about $250K. So you know, 10 times the funding, which allowed us to actually really do high fidelity engineering models to prove that we can do this. And so the way pulsar navigation works basically is we rely on the fact that some subset of the millisecond pulsars that we're looking at are reasonably good clocks. And if we can upload ephemerae of how these clocks drift with time, then we could use these clocks just like we use the atomic clocks of the GPS constellation. So you do trilateralization of where you are relative to the constellation. So you know, the idea is NICER would look at this pulsar and look at pulses coming from it. And if a pulse arrived a little earlier than expected, that meant you're a little closer to that pulsar and you have to adjust your orbit propagation model. And you do this in multiple directions and you can get a three-dimensional position of where you are. Part of our deal with the Space Technology Mission Directorate is to do this semi-autonomously on orbit. So our main electronics box, in addition to doing all of its other duties so that we can deliver the nicer science data that you all want, it also can run onboard pulsar navigation software. So at Goddard, we have a fantastic navigation team that have developed a lot of onboard algorithms for navigation that make use of a variety of information sources. We've added to the library pulsars as a tool to do pulsar navigation. We actually ingest the photons through our detector electronics called MPUs. We do some very simple event filtering on orbit autonomously. We batch process the photons to eke out a time of arrival for the pulses. That time of arrival is fed into an extended Kalman filter that's basically propagating our orbit model. And then we can send that where it thinks it is down to the Earth, and our GPS provides us very good truth data so we can test that. And so we're going to do this on station, and we have an opportunity to upload new data new algorithms at a different time, and of course all the data is archived regardless. So scientists can do equation of state science with the same data, while technologists can try to fine-tune their algorithms using the same archive for pulsar navigation. So when we launch, we've promised STMD that we're going to dedicate 2 weeks at the beginning of the mission to look at 5 or 6 of our target millisecond pulsars to do a demonstration as a concerted effort. We're still going to get science out of that time. And then toward the end of the mission, we're going to do another 2-week run after they had a chance to digest the performance. And again, we collect science through the whole period of time, and we just have some constraints to make sure that we can do a full demonstration early on. I'm going to get back to my modulated X-ray source again. So we have a modulated X-ray source. Where the heck is it? I've lost track of it. It was over here. We have a modulated X-ray source that was in this test bed looking at one of our EM detectors. We've developed some electronics so that we can simulate a pulsar light curve as seen from a spacecraft in a particular orbit, including orbit noise. The ISS is not the best orbit. It's a little atmospheric drag can make it a little less than smooth. And we can generate an arbitrary light curve, and this little purple fuzz is the raw output of one of our EM detectors, and you can see we're trying to simulate the Crab pulsar here. So you can do more than just pulses, you can do arbitrary curves. And so we've actually done full system testing of our pulsar navigation algorithms using that same modulated X-ray source we use for timing calibration cycle through for a few days our models for these 5 pulsars, okay, with realistic dead times between the objects. So you look at one for about 1,000 seconds, slew to another object for 1 or 2 minutes, track, look at this next object for a couple thousand seconds, and so on. And we've included in this program that we did in all the observing constraints, that would normally restrict us, and we put large initial errors, and what we found is that we could, with the full system, we can beat our requirement to STMD to get 10-kilometer three-dimensional knowledge of where you are in 14 days of integrating this extended Kalman filter model. We can actually do it in better than half a day. And when we turn off our X-ray source, you can see the model diverge at the end. So this data is actually available, and we're giving it out to our science team so they can practice their algorithms to analyze it. The spectrum is not particularly interesting because it's just an electron impact source, but it has all the other characteristics to kind of work out your data analysis tools, and so it's been fantastic for science as well. Again, part of our STMD project is to show that we could take what we learned from NICER and turn it into a package that's actually reasonable for a deep space mission. NICER weighs about 500 pounds. You don't want to put a 500-pound navigation instrument on something going to Pluto. So another side benefit of the fact that we had to build up our area with 56 detectors is we can actually throw out 55 of our detectors worth of data and just have one data set to actually see how our algorithms work with a very limited, sparse data set in a real realistic way. And we've already done some simulations, and so you can imagine that we have one of our optics in something the size of a large poster tube, and we modeled a Cassini cruise mission going out to Saturn, where we have good data on it. And so we modeled it from 2 to 7 AU distance from the sun, and we compared that Pulsar XNav is our other word for this performance against how it's normally done for deep space missions for NASA, which is we make use of the Deep Space Network and do ranging that's extremely good. We made an optimistic assumption of how much delta door time, where you actually take 2 of the Deep Space Network dishes and you try to get some extra data from that by comparing the position compared to quasars in the background. If we could get a day a week, which I think is optimistic. And so, this kind of optimistic but more standard way of doing deep space planetary navigation, we compare against the Pulsar navigation with a stripped down version of NICER. We find that we can quickly get to 10 kilometers in the simulation. It's more or less flat on our entire cruise out to Saturn, while the DSN method starts at about 20 and continues to grow the further you go away, as you can imagine it might. Now, that's still good enough for them to get captured into orbit and do science, but if you wanted to go out to Pluto, maybe you want to look at something like Pulsar navigation to get you there. I'm going to just summarize. I think NICER is going to deliver high visibility science on the space station. We're putting up an instrument with order of magnitude improvements in timing, energy, and sensitivity performance compared to RxDE. So I know we're going to produce a ton of papers with this. I think that we could be the biggest paper producer, peer-reviewed paper producer of any experiment on space station. I think this Pulsar navigation is something that's going to really connect with the public in a different way than a lot of our science missions normally connect. When I tell my mom about how we're going to do equation of state science, the eyes kind of glaze over. When I describe that we're going to do this Pulsar navigation and kind of how it works, she gets it. And so I think this is going to be a good hook, right, for why this is valuable. We are on track actually for a launch in August. But like I said, we're now looking significantly beyond that. I think we're still going to be delivering our payload down to Kennedy in June. We'll see what we can do to advance up the manifest for launch. We have a web page here with pictures and more information about the mission, as well as response matrices if you want to try modeling your favorite astrophysics sources. Thank you.
Thank you, Pete. Questions? Gary?
Can you say a few more words about how you go from the timing of an X-ray pulse to determining the diameter or radius of the neutron star? And is that somewhat invariant to the spin axis of the...
All right, so let me just start off. There are people who will answer much better than I can, but my science lead will. But we're doing light curve modeling, and so Slavko Bagnatov, who was here some time ago, developed a technique that we're using. We're also using some other techniques, but this technique is what we think is the most unbiased method. We make use of the fact that the modulation of the X-rays that you see from the pulsar. If you have a very large pulsar, then the compactness is different and you get less gravitational light bending, and so the depth of modulation is less. But if it's a little bit more compact, when the hot spot that you're looking at is looking away from you, strong gravity brings it back, and that's related to compactness, all right, mass to radius ratio. And so by looking at the modulation in conjunction with mass information, we get that radius. That's our primary technique, but there are other techniques.
What's that?
With the superb timing that you have and testing the GPS, is there a possibility that you would have enough information to take this even further and, say, determine whether any of these pulsars have an unseen companion like a planet or
Sure, that's
yeah. Like that, if there were gravity waves passing in the
absolutely. So there's the pulsar timing array science. Our instrument is capable of doing that type of work. We actually, I think, have an easier time than the radio astronomers trying to take out ionospheric delay terms. X-rays are well above the plasma frequency for all of those terms, and so we have, in some sense, a cleaner way of measuring the arrival time of the photons.
Are you going to be working with some of the radio people?
So we have actually people from the North American gravity wave nanograv team on board. We have a number. My deputy PI, Zavinar Zamani, is a pulsar radio astronomer by training. Scott Ransom. We have a number of people on board who are radio astronomers, and we are going to collaborate with them. Absolutely.
Yes, please.
Currently, what's limiting your time resolution? You said about 60 nanoseconds.
So,
best you can do.
Yeah, so what limits us on NICER, so the biggest component is drift speed of the electrons in the silicon drift detector. Okay, so round figures, it's 100-ish nanoseconds a millimeter. And so so if a photon interacts very far from the sensing anode, the charge has to drift some fraction of a millimeter, and that's, I think, the largest term. After that, it's going to be our GPS time standard. It's only good to about 30 nanoseconds.
Yes, please.
For implementing it for navigation beyond Saturn, if you take away the 55 of them, what does the rest of it weigh?
So yeah, so let me, I think I had that. So we feel, I mean, there's some room in how you do the mission system engineering, whether or not you're going to have your own, gimbal to point the thing, or if you can have the spacecraft actually do 3-axis pointing. But the core component is relatively light. I mean, the optics only weighs 300 grams, and I'm sure that we could push that a bit. The detectors don't weigh that much. You can use a carbon fiber structure to hold it together. So I don't think it's unrealistic to say that you could fit in a 4-kilogram, 4-watt swap.
Yes?
So you mentioned that the wax is somehow going to prevent it from becoming too cold while it's out in space. Can you say a little bit more how that works?
Oh, yeah. So, all right. So, yeah, I'm sorry. So our electronics boxes are sitting on top of these platforms, which are about the size of a big lasagna. Okay, it's a sealed box, and inside that box we have a wax that's been engineered so that it melts at -10 C. So it's a phase change material. So what we do is we melt that wax, and then if the power turns off, we have a lot of thermal inertia from the mass of everything else. It starts to cool down, but at some point you're going to take the energy out of the wax, right? So then, as the wax is slowly freezing, you get a few extra hours out of it. And so what we're trying to do is cross the finish line of 6 hours above our survival limits. And so that's where we get the wax. Does that answer your question?
You demonstrated that?
Yes. Yes. We do a lot of testing in this program.
Yes.
Martin? When you're doing the navigation, do you have to have a nice X-ray satellite somewhere always monitoring these sources in case they glitch in some way? Or?
Yeah, so like I said, we have a lot of radio astronomers involved, and so our plan is to regularly update the ephemerai of the pulsars that we want. So we have a table that we upload.
I was hoping you'd need a nice big X-ray.
Understood, yeah. Absolutely.
Okay. Sure. This place. I'll save my big programmatic question for the end. So it may not shock you to know that including the ISS in NASA's SMD AOs was not done through a democratic process. And so Keith and his team are among the bravest scientists who have waded into this very complicated other field with human spaceflight and STMD, and have done what looks like a really remarkable job. And I'm amazed at 54% observing efficiency. That's what Hubble does, and it's low Earth orbit. So the question is, when this was offered as a platform for doing science, the hope was, by not paying for a launch vehicle and not having a spacecraft bus, it would ultimately save money. And so if you had to fly nicer with its own spacecraft and a launch vehicle, do you think SMD overall is getting a good deal, even though it looks like you might have to deal with a launch delay of 6 or more months?
I think you're getting a good deal. I mean, it's a spacecraft bus will put you back. That's 3-axis pointed in the 30 to 50 million range. You have to build a ground system, and then the rest is for your instrument, and you have to have reserves on all of it, right? And so I think you are getting good bang for your buck on this particular experiment. I mean, having said that, there are challenges in working with space station. Human spaceflight safety, makes you do things that are a little different, but it's not all that impossible. When you get selected as a space station experiment, they hand you a stack of about 1,000 requirements that you have to comply with. Now, because we're going outside, that stack reduces to about 500, right? And of those 500, there's about a dozen that are contradictory. And so once you get past all of that, okay, yeah, I think it's a win. We're fitting within our budget. We did have, I say a lot of our infrastructure is in place. We found out just before our critical design review that, most of our avionics depend on 28 volts, and space station has a problem at the express logistic carrier sites with 28 volts, a potential problem. And they told us about 1 month before our critical design review. And so we had to actually come up with a solution that made use of the 120 volt DC power that's provided that we got gobs of. So we had to make our own converter to do that. And we fit that within our budget. Actually, Space Station funded us a little bit for that effort.
And your budget started out with the standard $50 million cost cap in constant year dollars. And then you had this augmentation from STMD and a little bit from
Yeah.
ISS, so you're about 75.
70 million, I was
Yeah.
72 million,
Yeah.
maybe, yeah,
Okay.
for everything.
Okay, yeah. Gary? Yeah.
The space station is not known to be the cleanest environment. Is that any problem?
So I'm going to just show you where we're at on the space station. Let me see if I can zip back here without it getting caught up on anything. In short, I'm not too concerned about it because where we're going on space station, and this is as good as any. On the other side, where we're going is where the DoD has been putting a lot of these experiments called the MISSI experiments, and basically they're contamination monitoring experiments. And so we have tons of data of how clean it is there. And in the early days, it was very dirty. Right? The Russian components had a lot of silicone on them. That silicone would come off. It would interact with materials. The atomic oxygen would mix and it would turn into glass. Now, over the years, that has been outgassing, and you can see that in the data. Since then, I know of a Navy experiment that's probably in one of the more dirtier places on space station with a UV instrument. They haven't seen any degradation. And then for nicer, we get an added bonus that kind of just below us, there's going to be the SAGE mission, which is going to have a bunch of quartz crystal monitors. It's going to monitor, in their data stream, the contamination as a function of time, which we could actually use in our calibration if we do see degradation in our response. So I'm not too concerned about it. The model suggests it doesn't actually affect our effective area in any major way at all.
Jeff, you had...
Well, did you, in getting through all of these complications to figure out how to do this, did you get help from any of the other science teams like Maxi or any of the other people that have worked ahead of you getting through all this?
Absolutely. I mean, we're standing on other people's efforts here. Maxi, was through Maxi that we learned about the gamma ray source. We made changes to our design that I think are going to make us better. Goddard has put together other experiments that go to space station. We learn a bit there, but we are a science instrument, which is different from most. And so we have different concerns. We've had it go other ways where, other experiments do something this way, but, they're just, at the end of the day, they're just a bunch of heaters, right? And not, it's a sensitive computer. And so we've done tests in a way that would work fine for a heater, but not for sensitive electronics. And so, you see this in the institutional knowledge of some of the engineers that are involved. And so we have to fine tune a few things, but absolutely we're learning from other missions.
I had a question about the mission duration. I don't know whether you mentioned this. And that leads into opportunities to point at targets other than the ones that are in your program. Is there going to be any general observer component to this?
Yeah, so we've been told that a guest observer program is approved. Mm-hmm. We're in the process of negotiating what the parameters of that and what our budget is for that and how that's going to work. Mm-hmm. Paul Hertz at headquarters is trying to sync us up with the senior review process. And with an August launch date, the timing was such that our baseline mission of 18 months would have finished 6 months before the next senior review cycle. So he offered 6 months so that you could get to that point and argue for an extension. So we have no expendables. The lifetime of our gimbals is probably longer than the space station. So we expect that we have no technical difficulties in achieving that. We just need to prove that this is a great instrument and that it's going to produce science that will be of value.
Yeah, terrific. Josh, that'll be the last question.
Your fantastic energy resolution and timing is, of course, as you've said a couple times, totally new phase space for doing spectroscopy in high time resolution on things like QPOs.
Yeah.
In both neutron stars and black holes.
Yes.
This would be fantastic stuff. Have you guys done all sorts of simulations?
We've actually been doing some simulations, and with the approval of our guest observer program, we've been told that after 1 year, if we're on good track with our level ones, at my discretion, we can start adding in other objects. So we have a science team that has a very broad depth, and we've started, and we call it the non-neutron star science group, but it's exactly for this type of stuff. And so yeah, we're going to get a few initial objects to do that, to whet the appetite and see if the general observers out there can use this instrument to do a little bit wider focused science.
I think we should bring the questions to a conclusion. There will be time for discussion afterwards or at dinner if any of you care to join us. So let's thank Keith again. At my office at 6 o'clock.
Thank you.
Deployed in a zero gravity environment, how fast can you close it down